Yes.
Well, actually, you will
Yes,
see
yes,
him
yes, I know him.
refer in this talk.
Okay.
Does he know you?
I I know him by name, but when I was doing my undergrad, I focused on probability and stochastic processes. So I don't remember having
Well, I will ask him, but Edilberto
any
is,
class with him.
well, remember, if you were a good student, he will remember you.
I don't
So
remember.
I'm not going to ask the question. I just leave it there.
Yeah, you can ask him. You can ask him.
Okay, good. Nice to meet you, by the way.
Nice to meet you.
So we'll just give it another minute or so, and then I'll start the introduction.
Well, you're the boss, Sunil, so.
Yeah, people can filter in.
Or should I call you Professor Rao now? We are.
No. More laid back. More laid back. Yeah. No, absolutely. Okay, let me start with the introductions, and then we'll let people continue to filter in. It's usually in the first 5 minutes that they can continue to filter in. Okay, so it's a great pleasure for me to introduce our seminar speaker in the Division of Biostats seminar series. As you know, we've done something a little bit different this semester. We've taken advantage of the power of Zoom, and we've reached out across the world. And our speaker today is an example. He's Dr. Vicente Nunez Anton from the University of the Basque Country in Bilbao, Spain. And I'll give you a little bit of background. So Vicente and I go back a number of years, I think to a conference in Dublin, Ireland. Way back when is when we first met. He is originally from Ecuador. Guayaquil, right? That's where you're from?
Correct. Yeah.
And he's a professor of statistics at the University of the Basque Country in Bilbao. It's part of the business school, is where his affiliation is with economics, mathematics, and what was the third one, Vicente?
Econometrics.
Okay. And he's now, as I just learned a few seconds ago, he's now the chair of the department, and he'll be doing his rotation as chair over the next number of years. He did his undergraduate training in Ecuador in electrical engineering, and then he came to the States and he did his master's in mathematical statistics and his PhD in statistics from the University of Iowa. His areas of interest are kind of broad, actually. He's worked in longitudinal data analysis, survival analysis, non-parametric estimation methods, goodness of fit testing, health-related quality of life methods, order-restricted testing, and over-dispersion modeling approaches. He's also published 2 textbooks, which is quite an accomplishment. So one is in what's called antidependence modeling for longitudinal data, and the other in non-parametric regression methods. He is very active on the international statistical scene. He's very involved with the International Biometric Conference. We were just talking about its location this year in Riga, Latvia, which will be interesting given everything that's going on in that part of the world. As well as the Statistical Modeling Society, where I believe he's the editor of that journal right now. And he's developed international collaborations for many, many years. He's been giving invited talks all over the world, from Europe to this US to Mexico and Latin America. And so it's a real pleasure to have him here. And he's going to speak to us about Bayesian spatial conditional over dispersion model proposals. So Vicente, I'll pass it over to you, and we'll go from there.
Okay, thank you, Sunil, and thanks for the invitation. It's a pleasure to be here, well, even online. And it's very nice to see you after some time. In case you're wondering about the pictures that appear in the first slide, the one on the left is the famous Guggenheim Museum that we have in Bilbao, with the pet that we have in front of the museum, which is called Poppy. And then on the right, you have the school I am now based with the University of Basque Country, have the different schools in different campuses. So this is just the business school, which is one of the campuses. It has a lot of students according to standards that you have in the US. So basically, an overview of the talk that I'm going to be giving today. First, I apologize if there are things that you are already aware of, but I didn't know that. So I'm going to try to introduce the topic to everyone so that everyone is aware of this. So I will talk about overdispersion first, and then introduce some of the well-known overdispersion models for spatial count data. Then we will talk about the proposals that we have made over the years on spatial conditional overdispersion models and the generalized version of them, which we did in 2018. And then we compared these models to the well-known Bézard-Yor-Mollier model, which is the one that most people use to model over dispersion on spatial data, and see how we do it in comparison to that, and what are the advantages and disadvantages we can have with regard to these models. And then we'll apply these models or the models that we are proposing and using, and compare their behavior to the one of the commonly used models by analyzing data from the Colombian infant mortality data sets that we have. We'll show you the fitted models, the results, motivate the results, interpret the results. We compare these to the Bézard-Yor-Mollier models I explained before. And then we'll also talk briefly about some things that we have been doing with people in Belgium, in Hasselt basically, about COVID-19 incidents in Flanders. And we'll show you the things that we have been doing with them. This is work in progress, but it will be interesting to see what you can do with regard to what they have done already. And then I will end the talk with some explanation of things about the current work that we have planned and the future extensions that we are working on. And then I'll provide some selected references for you in case you want to have them. In case anyone wishes to have a copy of papers or whatever, just email me and I will be glad to send whatever you need, okay? So first, talking about overdispersion. So as you know, GLM models assume that the response variable that we usually have, which is yi, I goes from 1 to n, follow a distribution, which can be normal, Poisson, binomial, or any other that is assumed. And in the Poisson regression model in particular, we let yi to follow a Poisson model with mean mu I, and we assume that mu I follows the regression model given by the equation you have on the screen. X is the vector of explanatory variables, and beta is the vector of unknown parameters that you have to estimate. Property known as equidispersion is present in this model, in which you all know that the expected value and the variance is equal to mu I. So when do you have overdispersion? Overdispersion is here when you have that the variance of yi is larger than mu I. You also have the phenomenon known as underdispersion, but this is not something I'm going to be talking about in this talk, okay? But you also have that. So the causes, speaking in general terms, without entering in a lot of details, the causes of overdispersion, we can have omission of relevant variables or terms in the model, as you usually could have in regression, non-constant variance of the response variable, or when the independence assumption does not hold, which is typical in a spatial data, which is the thing that we are actually talking about today. In this case, standard errors may be underestimated, and of course, the inferential processes may be incorrect. So you need to take this into account in order to obtain reliable inference processes for the estimated parameters in the models we are proposing. So the common overdispersion models that you have seen in the literature include at least two of them. First, the normal Poisson model, in which you have a random effect, nu I, holding a normal distribution with mean 0 and variance tau. And we assume that yi condition on this random effect follows a Poisson model. And then you have the regression model that we had before, but with the nu I added to the previous model, so that the variance can be approximated in this model as mu I plus tau mu I squared. And since the dispersion parameter is positive, that is tau is positive, then the variance is larger than mu I, which implies that this is a variance larger than the one specified for the Poisson model. So this model can be used to model over dispersion, which is the purpose here. But this is a well-known and used model. And then you have the negative binomial model, another possibility, in which we have the yi follows a negative binomial model with these two parameters that you have in there. And the mean is mu I follows the regression model given by the equation that we had before. And in this case, the variance is given by the expression mu I plus inverse of tau times mu I squared. And this is larger than also that they specified by the usual Poisson model, which means that we also can model over dispersion by using this model. Now, the data sets that motivate some of the things that we're doing, and I'm just going to go briefly to this is on the left, you have the infant mortality rates in Colombia for the year 2005. The rates were computed. This is by department in Colombia. And these were computed as the number of kids under 1 year of age who die per 1,000 kids born alive. And as you can see in the left graph that you can see that regions close to each other have the same color, which means that they have the same number of the same rates for mortality, and in a sense indicates that there's some type of a spatial relation between close by regions. And on the right-hand side, you have the COVID incidence in Flanders municipalities from September 2020 to January 2021, which was one of the difficult times when one of the changes of the virus attack again the population. And this is per 100,000 inhabitants in these municipalities. So again, a spatial correlation is present, or means that observations in locations that are close in space tend to show similar values, as it is the case here, and could be one of the causes for overdispersion. And of course, it must be taken into account. We'll come back to this data later in the talk. So first, let us talk about the spatial conditional overdispersion models that we proposed in 2018. Daniel, by the way, Edilberto and Edwin are both, well, Edilberto is a professor, but Edwin is a student in the UNAL. So in this case, we have yi represent counts for the n regions, and the spatial conditional model assumes that yi given y tilde I follows a conditional overdispersion distribution given by f of yi given yi tilde, and then yi tilde is defined as a set of values in all of the neighbors of the ith region except for the ith region itself. So we're looking at conditional distributions where you can keep the independence that you need to build the livelihood. And then the assumption is that the conditional mean follows a given regression structure as before that includes covariates, and also this is the spatial part that we're including, the spatial lag of the response variable with a spatial parameter that allows you to account for the intensity of the spatial correlation or dependence that you may have in the data. Now, how do you actually take care of model this dependence, a spatial dependence? Well, we usually use we normally specify this for a set of n regions by the n by n spatial weight matrix W, which elements wij, where the wij are the weights that represent the strength of the dependence between regions I and j. And you can define this in different ways. For example, the first thing is that wij are usually standardized by rows, so that we have the wij star, which are the ones that we are actually going to use, and they add up to 1. So for region I, wi times y is the spatial lag. This is what we refer to as the spatial lag of the response variable, defined as the product of the ith row of the W matrix and the response variables. So you have this weighted sum or weighted average of the response values at neighboring regions, but not at the ith region itself. And there are two main ways of specifying the wij in the literature: adjacency based on boundaries and distance. So depending on what you want to try or model, then we can use one or the other. So if you look at contiguity or adjacency, if you look at order 1 or what is labeled as order 1, then wij would be 1 if region j is adjacent or a neighbor of region I, and 0 otherwise. And one way of defining adjacency is by assuming that regions I and j are neighbors if they share at least 1 point in their boundaries. This has to be clearly defined because otherwise it can lead to some confusion. And then if you go to order 2, then it will be 1 the weight matrix coefficient. In this case, if they share a common neighbor, but they don't share a boundary, but they share a common neighbor. And then you can specify higher orders as you like. And now if you go to the distance specification, And if you label SI to be the center point or centroid of region I with coordinates XI, YI, then we could define the regions, the distance between regions I and J by this Euclidean distance you have there as Dij. This is the usual definition, so I'm not going to go into that too much. And the specifications of W based on distance will be inverse distance, which is the inverse of this Dij. Negative exponential is the exponential of the negative Dij. Distance mass in which you have the Wij is 1 if Dij is less than h for a chosen threshold h and 0 otherwise. And we'll use this distance band. This will be the best fitting model in the case of the Flanders data, as we will see later on. And for the mortality rate in Colombia, they will use the previous definitions based on neighboring for the Ws. So the spatial conditional dispersion models based on what we have just mentioned will be defined as follows. Well, we assume that the yi given yi tilde and nu I, which is the random coefficient, follows a Poisson distribution in which the conditional mean that you have there, conditional mean, follows the regression model. The difference with the previous model is that you have this raw wi term that we're adding to model the spatial association. And if you go to the spatial, conditional negative binomial model, then all that is changing is that you add this term to the regression model for the mean that we had before. Okay, so we have to estimate another parameter, which is rho in this case. Now, these models assume a constant over dispersion. By that, I mean that tau is a constant, but you can assume that tau is varying for the different departments or regions, and this will be the basis for defining the so-called generalized spatial conditional models, okay? Because there are cases in which this is required. So this is the generalized version of these models in which we keep the definitions that we have before, but then the difference here, or the addition here, is that you can also, besides what you had before, the only difference, the first one is that you have two equations now. The first one is the same that you had before, except for the fact that you put rho 1 instead of rho. And then the new I, which is a random effect, has a variance that changes with I, given by tau I. And in tau I, you model log of tau I because you want it to be positive as a regression model as well, in which you can include covariates in the first part, the say I prime gamma, and then you have another term which is similar to the previous one, in which you have, or you can have that the dispersion also changes spatially. And then this interpretation, the basic or general interpretation of the parameters rho 1 and rho 2 will be a way to explain the strength of the spatial association in both the mean and dispersion parameters respectively. Okay, so what about a few details about the Bayesian framework thing? So we have the end independence observation as already mentioned. The parameter is theta, so we express our belief via prior distribution, and we want to carry out inference about this using the information in the data. How? We update our knowledge of theta using the Bayes theorem, the usual thing. We have to obtain the posterior distribution and use this to make inference. That's what we do here. So very often the posterior is intractable. In fact, in some of these cases it is. So we have to use computational methods such as MCMC, INGLA, and software, different types of software that we use here, JAX, Winbox, INGLA, Stang, Nimble, and a variety of our software packages. If no prior information is available, then we use vague of non-informative priors, okay? Now let's go to the data sets that we are going to talk about. So the first one is the study of the infant mortality rates in Colombia, as I already explained. The variables available for each of the 32 departments or regions are the number of children under 1 year of age who died in 2005, that's the variable ND. MB will be the total number of births, so that the rates can be computed as the ratio for ND and MB times 1,000 per 1,000 children. That's what I mentioned before. IBM will be the index representing the percentage of the population with basic needs not being satisfactorily attended. REC, resources in thousands of dollars provided by the government per household for academic achievement or education and integral attention for children and young people. The variable BO is the percentage of women over the age of 18 who has suffered physical violence from their current partners. HE will be the percentage of people between 18 and 24 years who had access to a higher education level. And BAT finally is the percentage of children under 1 year of age who received the third dose of the polio vaccine in the year 2004. So these are the variables we have available for our models. So the next thing would be to use these models that we have proposed before to fit this data. Before that, we will try to motivate the need for these over dispersion models. So the aim here is to study mortality rates, capturing and being able to explain over dispersion and spatial association. This is the observed data on the left, and on the right, we have the test that we use for a spatial association, Moran's test. The Moran's test value, test statistic was 0.3490 with a p-value indicating that there is evidence that you have a spatial association, positive spatial association in this data set. Actually, Moran's plot that you see now is the mortality rates on the X, on the horizontal X, and on the vertical axis, you have the spatial lag rates. And as you can see, there seems to be some relation between these two. And Moran's coefficient or test statistic is actually the slope of this line that you see in red in the graph. If you don't trust Moran's test for whatever reason, we have also carried out Gary's test for the same thing, and there is evidence, statistical evidence of a spatial association, positive one. So once we know that, the next step will be to fit some of these models. So the models will be the same ones we have proposed before, but with the variables in there. So we fitted the Poisson model, a spatial conditional Poisson model, the normal Poisson model, and also the spatial conditional normal Poisson model. These are just the variables and the specification for the models. And then we also fitted the negative binomial model with the variables in there, and the spatial conditional negative binomial model. Before that, it would be a good idea, of course, remember that the spatial conditional models include these lag variables in the model. That's the difference between the previous models and these models. So for the Bayesian estimation, some details about what we have done and assumed. Specify non-informative prior distribution for all the regression parameters. The beta J's will be assumed to have a normal distribution with mean equal to 0 and variance equal to the number you have there. Okay, rho will also have the same distribution, the rho parameter in the models. And then for the inverse of the dispersion parameter, we assume a gamma distribution with those parameters. We also perform, as usual, a sensitivity analysis, considering different values for alpha from 0.1 to 1 times 10 to the minus a, to make sure that the prior will not affect posterior inference. And the selected values are the ones at which everything is stable in terms of estimation and standard deviations. We have used open box and JAX for the MCMC approach, and INGLA, the software INGLA for the others. And the model comparison and selection was carried out by deviance information criteria and also the Watanabe-Akaike information criteria, which is kind of on fashion now, where in the form of lowest values indicate better fit. And we have also performed a posterior predictive check to see if the models were doing okay. Now, let's first motivate the need for these over dispersion models, as I mentioned before. So if you feed the Poisson model, don't pay too much attention to the estimates now, because this is a previous model that is not actually a good model, but this will be the standard, the coefficients and standard deviations at 95% credible intervals, and the values for DIC and WIC for this model. So if you take these models and you want to know if there is overdispersion or not, then you plot the estimation of mu I, and that should be approximately equal to the estimated variance, which is yi minus mu I hat squared. And if you plot these things, then you see this plot, and this plot basically tells you that most points are above the red line, and that suggests overdispersion. So basically, you need to fit models with overdispersion. So we now know that we have to fit models with overdispersion. And in addition, we also know that there's some spatial association in the data. So this is suggesting that we should fit one of these models and see how the model does actually. So let's do that. So this is the fit for the normal Poisson model so that you can see the results. I will interpret the coefficients in a minute, so don't worry too much about details. But the important issue here is to see the change that we have in DIC and WIC going from the previous model 491 and 524 to 308 to 302, excuse me. So this is a very significant reduction in terms of fitting model, okay? So this is a simple overdispersion model with no spatial association included in the model. So we have also fitted the other models, and this is what we have as the results. So the Poisson model, the spatial conditional Poisson model, normal Poisson, negative binomial, and the other ones. And look at the DIC and WIC goodness of fit criteria. So it seems to be the case that model with the lowest information criteria values is a spatial conditional normal Poisson model. That is the one that has the lowest one. Well, you can use the normal Poisson also as a competitor, but the other ones are not doing very well. And then we carry out some variable selection, taking into account information criteria values and posterior predictive checks. And the final model, the reduced model for the spatial conditional normal Poisson model, which was the best one, as we already decided, is the one including these variables, IVN and REC in the mean model, and then you have the spatial part in the model. And then we also have here the constant over dispersion so far. And then we have some reduction in terms of DIC and WIC with respect to the previous models. Now, some interpretation that is important to understand with regard to this model and the variables that were selected. So the estimated coefficient for IBN is positive, and this variable is significant according to the 95% credible interval. This, in general terms, it means that mortality rate increases in regions where the percentage of the population not having basic services unsatisfactorily attended is larger. This makes sense. So this is important. It has to make sense. What about REC? Well, the estimated coefficient for REC is negative, as it should be or is expected to be, and this variable is also statistically significant, and that kind of means that the infant mortality rate decreases in regions where the more resources are provided by the government for education. Also makes sense. The estimated coefficient for the spatial term is positive, and this variable is also significant, and there's some evidence of the presence of positive spatial autocorrelation in the data. So the next question is, so do we need to make this non-constant dispersion or take into account that? That means, do we want to consider the generalized version of these models? So that's the next thing. So we also fitted these models, and the best model was the generalized spatial conditional normal Poisson model, and the reduced version of this model included these variables. Now, this is kind of different in terms of goodness of fit fitting, is kind of similar to the previous one, but this model is different because it does not include some of the variables, although the variables are all that we have in the mean model, but instead we have one of the variables went to the dispersion model or the dispersion parameter model. So you can actually indicate that these two models are good models of fit this data in terms of, we'll see how good or bad they are doing in terms of posterior predictive checks and other things in a minute, but these are good models for fitting this data. So interpretation about this, now again, look at the mean model, we only have the lag variables there, the spatial ones, and in the dispersion, we have the variable IBN. So the coefficient of the variable IBN in the dispersion model was positive and is significant as well. And this is can be interpreted as saying that the dispersion varies according to the variable IBN in such a way that in regions where the percentage of the population not having basic services satisfactorily attended is larger, the dispersion increases. And that makes sense, at least to the people handling this data set. And also the spatial parameter keeps being positive in the mean model, and the interpretation is the same that we had before. So besides being able to properly capture the spatial dependence in the data, this model also explains the non-constant dispersion, and it seems to be or provide a good fit to this data. Now, if we want to compare these two models in terms of posterior predicted checks, we can look at the scatter plots from the observed to the predicted rates obtained from some of these models for this data. On the left, you have the best model that didn't consider the dispersion to change with I, or to vary across departments or regions. And on the right, you have the generalized spatial conditional normal Poisson model in which you allow for that. So it seems to be the case. Well, both models are okay, but the one on the right, the generalized one, seems to be doing better in terms of this. So that's one thing that you can consider. Now, in terms of predicting actually the rates that we observe, then on the left, you have the observed rates, and then you have in the center, the model without having the change in dispersion. And on the right, the model where you have the dispersion changing. And then, well, if you don't pay too much attention, you can look at this graph and say, well, they are quite similar. But there's one small region, I don't know if you can see me pointing at this, in this part, where this model, the generalized one, is not predicting well here, whereas this other model is predicting quite well everything in every region. So the spatial conditional normal Poisson model is predicting everything as it was observed in the data, whereas the other one in one of the regions is not doing the well. Actually, two of the regions, because there's one here and one here. So two of the regions are not being predicted in the right way. Now, well, it is up to the practitioner, the user, to decide which model is the one that could be used. As Box used to say, there are no correct models, it's just useful models. So these are useful models, and you can decide which one is more useful to you in this sense. What about the comparisons to the Bézak-Yor-Mollier models that are the most commonly used models in spatial data in general? Everyone, if you present some fitting of models with any other method you're proposing, will tell you to compare your models to these models. So we had to compare that, actually, because a referee asked for it, so we had to do it. So in this case, the assumption for this BYM model, I will explain why you need the second model in a minute. Then is the YI condition on the random effects, because you have two random effects. It follows a Poisson distribution with mean mu I, and then the conditional mean mu I is given by this equation. The first part of the equation is the usual explanatory variables multiplied by the coefficient that you have to estimate, and then you have two random effects. And mu I is assumed to have a normal distribution with mean zero and variance tau. And this is the unstructured random effects that you usually have and that you had in the normal Poisson model, for example. Whereas eta I is a spatially structured effect that follows an intrinsic conditional autoregressive model, a CARB model distribution. And then the problem here, as most people using this model indicates, is identifiability, because it seems to be difficult to make a difference between the unstructured and the spatially structured random effect. So they seem to be confounded. And this is why they proposed at that time the BYM model or the Bézak-Yor-Mollier 2 model, which is an extension of this model that scales the spatial component and the structure component so that the mean regression can be given by this not so nice looking equation. What you have to look at basically is this 5S thing is the one that tells you what part of this is unstructured and what part of this is spatial. And then the other one, the tau S, is just scaling the variance. So if you fit this model in here, you will get, this is the reduced model. So you have the two variables that we had before in the spatial normal Poisson model, okay? And these are the coefficients you have. And basically DIC and WIC are very similar to the ones we obtained before. And so the fit is similar to one we have for the spatial condition normal Poisson model in terms of information criteria, and the interpretation of the variables is the same or similar. So in this case, only the variable IBN is significant because the other variable is not significant according to the 95% confidence interval. And the spatial conditional normally both of them were significant. That's one difference. The two variables come in, but one of them is not significant. And then also the estimated variance parameter for both the spatially correlated and the uncorrelated random effects show overall quite large standard deviations for these type of models. These are large standard deviations for the tau, eta, and tau estimators of the variances in the random effects, making it difficult to interpret them, especially to explain the spatial dependence or the extra variability present in the data. So that's why we decided to also fit the BYM2 model, in which you have that nu I and eta I have variance approximately equal to 1, and tau S captures the variance contribution from the sum of the two random effects, and phi S, as I mentioned before, controls the variance contribution of the spatial effect eta I and the variance contribution of the unstructured effect nu I, and this is explained by 1 minus phi S in one case and phi S in the other. In terms of goodness of fit, it is very similar to the one we have before. Now, again, IBN is significant and REC is not significant in this case, as it was before, and it was for the normal Poisson condition, spatial condition normal Poisson model. We had both variables being significant. But in terms of being a good fit, I mean, all of these models are a good fit, but it depends on the fact that if you want variables to be included in the model or not, well, that's up to you. And then we have to look at posterior checks and prediction in the graph of the mortality rates and see how these models are doing. And the parameters phi s associated to the amount of variability captured by the spatial structure considered in the model explains more than 30% of the variability. That's important. And this is an advantage over the BYM model because you can actually identify the contribution of each of the random effects, which you couldn't do in the previous model, the previous BYM model, not in our model. This is a different interpretation for the models. Now, we have fitted both of these models, as I mentioned before, but they do not offer really improvement in terms of DIC and WIC when compared to the spatial conditional models or the generalized models, and do not offer improvement in terms of posterior predictive check. You have the posterior predictive checks graphing here, and they don't look quite good at the end, as you can see. And if you look at the predictions of this model with regard to the observed data that we have, again, they do okay, but there are regions in which they don't predict very well, especially in the smaller regions. So, well, again, it is up to the practitioner, the user, to decide which ones to use. And these models are not so easy to fit because of convergence in most of the Bayesian software packages that we have, whereas the others we are proposing, they were okay. I mean, we just have to program things and they were working okay. Okay, so this is in terms of mortality data, and then we can move on if it's okay. I think we are right on the time that I was planning to the next part of the talk, which is shorter because we're still working with this, and I should mention that this is a joint work with Professor Crystal Fives from Hasselt University. And I forgot to mention something that it was very important, that this is a joint work with Mabel Morales Otero, which is my PhD student. Mabel is finishing her PhD thesis this year, and she spent 3 months at Hasselt working with Crystal, because in Spain, in order to have a special mention to the PhD you obtain, you have to spend at least 3 months in an abroad university, and she did it in Hasselt. Okay, so in this case, you don't have covariance for this data. They don't have covariance for the data. We could have covariance, but we didn't have covariance, so we have to go. And they have fitted models without covariance and analyze this data. And then when Mabel came in and showed them the data that we were, the models that we were using, then they were interested in trying to see if these models were good fit for their data. So what we have here is we have variables available for 300 municipalities, and the variables that we have are N cases. This is the number of COVID-19 cases in each municipality from September 2020 to January 2021, the population in each municipality, so that the incidence can be obtained as the number of cases divided by the population times 100,000 inhabitants. And we can also obtain the standardized incidence ratio, which is SIR, for each of the regions as the number of cases divided by EI, where EI is what they define in Hasselt. This is not us, this is them, but in any case, it is an interesting thing and useful one. It's expected counts if the population in the specific region behave as the standard or overall population does. That is, using indirect standardization, you can define EI as the product between R to S times PI, and you can use also age or gender. And RS is the rate of the entire population, so that RS is the sum of the number of cases divided by the sum of the population. Okay, so this is the math of the SIR for the regions that we have, and the municipality that we have in there. And then anywhere you have that larger than 1, that is the darker regions, that indicates that a larger incidence than expected in region I. And if you have SIR I less than 1, that indicates lower than expected. So these are the ones that are doing kind of okay, but the darker ones are the ones that not doing very well. Okay, so what are the fitted models we have? Well, the SIRs do not take into account a spatial association. So they are sensible to extreme values given by small areas. So a solution could be to estimate relative risk of the disease for each region via spatial regression model. So we are talking about relative risk, and the relative risk represents the risk of infections for the population in the ith region relative to the risk of the population in general in the whole area of Flanders. In this way, we can include covariance and information about neighboring areas using the models we already mentioned before. So the fitted models would be, I'm just going to go to the model that we use as the best fitting model. So this is the spatial conditional normal Poisson model for the relative risk theta I, in which the number of cases for the ith region condition on the number of cases for neighboring regions And EI and NUI follow a Poisson distribution. And the mean is given by EI times theta I, so that you can write the first regression model. And then after simplifying, that becomes the last model, which is the one we're fitting. As I mentioned before, we don't have covariates. So we have the lag variables and we have the NUI. And then the question is, how do you specify the W matrix? And this is one of the things that we're interested in doing. So we can model and estimate relative risk. We could also include covariates to evaluate the risk factors and so on. We don't have covariates now. So the different possibilities that we consider for the W matrix, remember in the mortality rate data, we just use order 1 contiguity. So here we're using contiguity of order 1, order 3, inverse distance, negative exponential, distance bands, minimum distance that ensures that all regions have at least one neighbor. And this minimum distance, that is the age that I mentioned earlier in the talk, was of 17.57 kilometers approximately for this specific case study. So we have fitted these models for each of these spatial wave matrix considered, and including the spatial lags that we have mentioned before in the model. Another connectivity structure that they have suggested and that we can use is the so-called mobility matrix, in which MIJ, which is replacing the WIJ matrix or the W matrix, it will be the mean proportion of time people from municipality I have spent in municipality J from September to December 2020. This is at the worst part of the COVID thing in Belgium. So it is standardized by rows, so that the MI times the incidence can be considered as an average of the incidence in the municipalities where people move into, weighted by the mean proportion of time they spend there. And the model we are fitting is the one you have below, but instead of having the W matrix, we have the M matrix in here. Now let's see how these models fitted. So these are the results of the models that we have. We don't have covariates again, so we just can interpret the models in terms of goodness of fit. So as you can see, these are all the models that we have mentioned before, the DIC and WIC values. So the model with the lowest information criteria values is where W following the distance band specification. Okay, that's the one that we have here. These are the estimated parameters that we have. We only have beta here, rho, and then the dispersion estimation. And these are the DIC and WIC estimated for each of the models that we're putting into this table for contiguity of order 1, distance band, and mobility. These are the ones or the models that have a similar fit in case you want to know why they are the ones included here. But this is probably the important issue interpreting these things. For the free fitted models, the estimated parameter or intercept beta are negative and statistically significant according to this thing. The estimated spatial coefficients are positive, and the spatial lags are statistically significant according to the credible intervals. This is kind of indicating that the presence of positive spatial correlation is appropriately captured by these terms. And that also means that regions with a high or low relative risk of infection will be surrounded by regions with a high or low risk as well, which is good to know. But we knew this, but we had to model it. And the estimated variances or the random effects in general are small for the three-fitted model, suggesting that there's not much unstructured variability left after taking into account the spatial dependence in the models by including the spatial lags. So this looks okay. Now, these are the maps. I'm sorry that I cannot show you the maps for all regions together, but these are larger maps, and this is difficult. So this is the prediction map for the contiguity of order 1, for the distance bands, and the for mobility. And as you can see, there are changes, of course. So these models are not equivalent or the same, and as we expect to have changes, but the main things are predicted appropriately. And then we can also look at people in Hassel were interested also in looking, and this is for governance reasons. I mean, they want to instate public health policies in there, depending on where they were. So we can talk about the exceedance probabilities, which is defined as the probability of theta I, the relative risk larger than C. That's the probability of the estimated relative risk of a region being greater than a given value C. And what do you need this for? Well, it will indicate how likely the risk is to exceed the value C, will help you identify areas with an unusual elevated risk, and will also tell you which regions should be examined more closely and where should public health policies be applied. So this is quite important for them. So the fitted model results for this, when C is equal to 1, So this is a contiguity of order 1. Now, the important thing to keep in mind is that darker regions means that the risk is very, very likely to exceed 1. So these are regions where you have to be careful with. If the government wishes to do something, these are the regions where they want to do something about. And what is being predicted by these models with contiguity of order 1, distance span, or mobility are very similar, except for some small regions or some small things where they changes. Now, what are we currently trying to work on? Well, we have already defined or developed a spatial conditional but dispersion models for binomially distributed responses and the generalized extensions. So whatever we did for the Poisson distributed responses, we did it for the binomial. We have already extended this to temporal. So we have a spatial temporal models for all of these previous models, following the ideas in the paper that we wrote with Edilberto and Edwin, but for temporal autocorrelation as well. And then with Maria Durban at University Carlos III, we are working, well, we have already worked on that, but we just have to write this down, on semi-parametric extensions that allow for nonlinear relations among the response and covariates using p-splines and mixed models. With Crystal Files, which is the one that I just mentioned or presented some of the preliminary work, we are constructing weight matrices that are not based on contiguity or distance, but instead reflect socioeconomic characteristics for similar regions. This is work in progress. We hope to finish this in the next couple of months. That is based on differences among the values of specific covariates, interactions with the standard spatial weight matrix, application to COVID incidence rates in Flanders municipalities, as we did before. And then recently with Virgilio Gomez Rubio from University Castilla-La Mancha here in Spain, we have worked on generalized over dispersion models because they cannot be fitted in INLA. And INLA is well used, so this is more a computational paper. So we have proposed a way to fit these models by fitting double hierarchical generalized linear models in INLA with the importance samplings algorithm. And this is finished and has been submitted to a journal, but we haven't heard from the journal because it was recently submitted to the journal. And if you want to have some references that I have been mentioning or talking about in this talk, there you have it. I usually assume that the talk should last about 45 minutes or so that in case people have questions, they will have time to do that. If they don't have questions, then we can talk about the weather in Miami and the weather in Bilbao, which are quite different because it's cold over here. So, and I presume that it's not cold over there. So thank you very much for your attention. And there's my email address in case you want to ask for something or you need to ask something from me. And that's it.